This talk is about runtime verification based on register automata. I'm Radu Grigore. The work was done together with Dino Di Stefano, Rasmus Petersen and Nikos Savelakos. So, what are register automata? Well, everybody knows regular languages because they're useful, they're simple, they have some nice properties such as closure under various operations. They also have some not so nice properties. For example, every regular language has a finite alphabet. You can see this by thinking of how regular languages are represented. There are two standard ways to do it: finite automata and regular expressions. So let's take regular expressions, and I'm talking about a usual mathematical one where atoms are letters, and you have three operators: sequencing, clean star, and alternation. Now think of a word that matches a regular expression. Every letter in that word must appear somewhere in the regular expression. So because the regular expression is finite in size, that means that all the letters come from some finite set. Therefore, the alphabet is finite. So in the 90s, some people thought that this is not a very nice property. Let's see if we can have some class of languages which do mention infinite alphabets, but they're as similar as possible with regular languages, meaning that they retain as many of the nice properties of regular languages as possible. And the way they did it was they said, let's take one of the representations for regular languages, namely finite automata, and load them with some memory such that when a letter comes, this register automata can choose to store it in a register to later compare it with a subsequent input and decide based on the result of that comparison what to do. And say that quasi-regular languages are exactly the languages recognized by these machines. That was one part of the story. What's the other part of the story? Well, the other part of the story is runtime verification for Java. And here people run a program and they look at some abstraction of the execution, some sequence of events. And usually the events they're interested in are things like method calls and returns. It could be writes to fields, reads from fields, but it's not that important. So let's say it's method calls and returns. Well, the events contain something like a tag, call, return, so comes from a finite set, a string, like which is the name of the method. This also comes from a finite set because the program text is finite, and this is true at least if there is no reflection. But you also have values, references to objects, for example in the arguments, and these conceptually come from an infinite set because there is no a priori bound on how many objects you can instantiate during the execution of a Java program. So they have the same problem. They have to deal with infinite alphabets. They call this problem by another name. They say they do parametric monitoring, but it's exactly the same. And they came up with different solutions. One that is fairly nice, and especially the description in this paper from 2012 is nice. It's called slicing. That means that you pick a group of objects you're interested in, you retain all the events that do not talk about other objects, talk only about this group of objects you're interested in, and then you drop the values from these events and you keep only the method names. Now you have a word over a finite alphabet, and you can feed it into any formalism that handles finite alphabets, such as regular languages, finite automaton or something else, but you can also choose another formalism. Anyway, we notice that there is this pre-existing solution to the problem of infinite alphabets, a register automata, and we notice that compared to slicing, there is at least some properties that you can express and slicing cannot. For example, taint properties. In contain properties, you have some source of dirty data. There's some way to derive new data out of old data, and then some ways in which you're not supposed to use the dirty data. So a typical example is that if a string comes from a web form, then it's dirty. The way to derive new data from old data would be string concatenation, and then you're not allowed to use dirty data to construct an SQL query, to run an SQL query, for example. So because we saw that there's at least some advantages of this register automata, we said, well, let's see if we can use that as a basis for runtime verification. And we can. So let me give you a demo. In this directory there's 3 pieces of information. Let's start with the Java program, which creates a collection, adds an element to it, and then uses an iterator to access that element. If I compile this program and run it, it prints the element without giving any error. However, conceptually there's something wrong with this property. Why is there something wrong? Well, because if you create an iterator on some collection and then you immediately call next on that's not supposed to be something you should do in most situations. Before calling next, you are supposed to call HasNext. That's supposed to return true, and then it's okay to call the next method, but only once. After you call it, you go back to this invalid state where you cannot call next, but you can call HasNext. So that's how you're supposed to use iterators in Java, and yet you don't get any error. You don't get an error because it's an expensive check. However, during testing, for example, you would like to make sure that you don't have this problem in your program. So how do you do it? Well, in this directory I have the standard library of Java. The property was talking about the standard library of Java. So what we do is we instrument the standard library using the property HasNext. I hide some debugging output. And while this runs, we continue with the presentation. We'll come back to it. So what you saw is this tool architecture. You have a program, in this case the standard Java standard library, a property that talks about that program. You feed both into the TOPL compiler. TOPL is the name of a variant of register automata and of the language that you saw in which the property is written. The output is gonna be 2 pieces of information. It's gonna be an instrumented program which at runtime emits events towards a monitor. The monitor is an automata encoding of the property plus an interpreter for that automaton. When the error state is reached, it will log a message, and otherwise it does not affect how the program runs. So when we set out to do this to show that register automata can be used for runtime verification, we had a few goals in mind. So one was to show that it is relatively easy to use, that it's user friendly. It's not that it's possible in principle. We wanted to see that it's also convenient, so the programmer does not have to do some crazy things to use it. But this user friendly thing is a very subjective notion, so we had to concretize it a little bit. What we said is this: well, we're gonna have this automata representation and we're gonna have some labels put on the edges, and what we want is that if you take some path from start to error and you put these labels one below the other, you should get something that looks like a Java program, that is very similar to a Java program. So that was our criteria. We wanted to have this. Now on the other hand, we wanted to make sure that we keep the expressiveness of register automata, because we knew there are some things that they can say that slicing cannot. So we wanted to make sure we're exactly as expressive. Also because we didn't want to study all these closure and decidability properties all over again. We wanted to be able to reuse all the results from register automata, so we did not want to invent a wildly new device. Okay, this one finished. Let's see what it produced. It produced the instrumented directory, which contains the instrument Java library and the monitor, the TOPL monitor. Now we have to edit this file a little bit just to say start monitoring, stop monitoring. I'm gonna compile it again, and now I have to say using this class path. Okay, and now if I run it, we get an error trace which says, well, this event happened, so I went to the invalid state, and then this event happened, and then I went to error state. So it tells you what's wrong. Now by editing a little bit the monitors, there's one file with settings. I can show it to you. Instrumented TOPL property, the Java, and has this set of properties. You can say, for example, keep longer traces or smaller traces, keep also line numbers and the whole call stack, and so on. So there's a few more things that you can get out of these traces. Okay, how did that work? Well, here's a picture of how we specified the property that you saw earlier for slicing. It's slightly different than the HasNext property, which I ran, but it has the advantage that it fits on one slide. So this one says it's bad to call the method next twice in a row on the same iterator unless there's an intermediate call to HasNext. And you can see that this is a direct graphical representation of the textual representation that the tool processes. The first thing that happens is that this gets translated into a representation where each transition is labeled by a pair guard action. So, for example, the first transition says, I'm talking about the method next. That gets translated to the guard that says that element 1 of the store, which in this case is next, it's fixed, must be equal the component 1 of the letter. In the trace that is given here as an example, the first event has the first component equal to HasNext, so the guard evaluates to false. The second event has the first component equal to next, so the guard will evaluate to true for this event. When if the guard evaluates to true, the transition is taken, and then the action is executed. The action is an assignment that says take the second component of the letter, which is some reference to an object, and put it in the third component of the store, where 3 is just how we're going to call what used to be called I in this representation. Okay, next step is that we use a slightly less redundant notation because this SL appear all the time, so they have to have that shape. And finally, there are some things that I'm not going to talk about. What I presented here is example, the low level TOPL automaton. The high level one has some extra conventions. For example, if you are in some state and the guards of all outgoing transitions evaluate to false, in the low level automaton you get stuck, which is what happens in normal automaton. In the high level automata you have some skip semantics, which means ignore this event and just continue processing with the next one. Okay, the plan now is this. We have this TOPL automata, and I told you informally about register automata. We want to show that they have the same expressiveness, that you can translate between them. So to do this formally we need to define both of them in sort of a common framework, and then we can do proofs. What is this common framework? Well, one thing that is different from what you do in general is that letters are gonna be tuples, so that it better matches what happens in the Java case. Tuples of n elements, and what we will store in the memory are gonna be values, so are gonna be components of the letters rather than letters themselves. That's a little bit different than what you normally do in register automata. And the other thing that is different from finite automata, at least, is that transitions are labeled by a pair of guard and an action rather than by letters. Now, I didn't say much about guards and actions. Let's try to rectify that a little bit. About guards, in general, in this some abstract level, we only care about the fact that they come with some satisfaction relation which works on stores and letters. So given the current state of the memory and the current letter, you can tell whether guard holds or not. I don't care how that works, but the point is that when we specialize this to register automata and to TOPL automata, we'll have to define how this works. We'll have to define the satisfaction relation. Actions are just assignments which do what you'd expect them to do. They take one component of the letter, the jth component, and they put it in one register, in register I. You can also have sequences of assignments. And now with this notation, the definition is easy. It's like for finite automata, except that instead of having only an initial state, you also have an initial store. And instead of having letters on transitions, we have these labels, which are guards and actions on transitions. Then, to define the semantics, we define this infinite configuration graph. We start with a finite automaton and we build an infinite configuration graph. How do we do it? Well, we look at each transition in part of the automaton. This is fairly standard. And we enumerate all the models of the guard. For each model, we create a transition in the configuration graph, an arc in the configuration graph. We label that by a letter, and we compute the resulting store using the action from the model of the guard. Sorry, the action from here, from the transition in the automaton. So you see, we start with some finite representation that has guards and actions, and we go to an infinite representation which has arcs labeled by letters like in finite automata. Finally, we can define register automata in this setting. We put these extra constraints. The alphabet must be unary, so letters are values. There are two types of guards. One says the current letter must not be in any register. That's fresh. And the other one says the current letter must equal what we have in register I. Furthermore, there's two extra restrictions on how to combine guards with actions. For example, you can, if you use the guard fresh, then you must have exactly one assignment. If you use the guard equals I, then you must have exactly 0 assignments. There are some variants of the definition that relax these constraints, but the most standard, the one most used, I think, is the one here. It corresponds to the one we have here. Notice that if you start with a store that contains no repeated values, then you'll always have no repeated values in the store. That's because whenever you write something, whenever you set a register, you first check that it is fresh, that the value is fresh, that it does not appear already there. Now you don't have that kind of property for TOPL Automata, so that's why when you translate between them you need to do some work at least. And you don't have the constraint about the alphabet either. The guards are a little bit more symmetric. Of course, they need to talk about the to have two parameters, I and j. They need the j because they need to identify a component of the letter, because now the letters are tuples. But instead of having equals one register different from all registers, you have equals one register different from one register, and then conjunctions of these things. So now with this is set up like this in this common framework, we can prove the following result. And as I should say, this is about high-level TOPL automata. So one part of the result says if you start with this TOPL automaton, high level 1, you can build an equivalent register automaton with some growth. I mean, when you see this definition, it looks like, yeah, it must be possible. But then there are some problems. One problem is the one I told you with repeated values in the store. You need to solve that somehow. In a register automaton, you cannot have repeated values. So you need to simulate it somehow. That's one problem. Another problem that in this high-level automaton you have skip semantics, and then you also have a mechanism to enforce that two events are exactly one after the other one to compensate for this skip semantics. So at some point you might want to say this must be one after the other, and you're not allowed to skip it at this point. So to handle these things, there's some technical complications. But anyway, the point is that it can be done. And because there are constructive transformations from TOPL automata to register automata, all the results about expressivity, closure, and decidability that are known for register automata are inherited by TOPL automata. So let's see. We know that register automata are closed under sequencing clean star alternation. So TOPL automata are also closed under this operation. We know that the non-emptiness problem of register automata is decidable. That means that if someone gives us a TOPL property and asks if there exists a program that makes it fail, then we can decide that. We know that universality and language inclusion is undecidable for register automata. So that means that if someone gives us two properties and says, oh, this one is supposed to be a refinement of this other one, meaning that whenever the first one fails, the second one is supposed to fail, and ask us if we can check that automatically, then we know the answer is no. And so on. So we can we know that register automata are not closed under complementation, so that means that in some cases we might be able to specify what's bad behavior, but we cannot write down a property that specifies what's good behavior, and the other way around. So that means it might be good in a tool to have both ways of specifications, and so on. So now it's time to summarize what you saw. What did we do? Well, we saw the essential problem is infinite alphabets. that they have this problem in runtime verification. And we know that there's a bunch of automata that handle this problem. Maybe we can use some of those solutions. There is register automata, data automata, PEBL automata, and other kinds of automata. We took just the most standard one, register automata, and we said let's use it. To do so, we designed this TOPL automata, which make it possible to write properties in a user-friendly way. You write a property in a way that looks very much like a Java program. And yet we made sure when we designed them that we can still translate between them and register automata, so that we inherit all the nice properties of register automata. So, for example, the closure under sequencing, alternation, and cleaning star implies that we could also have a regular expression like representation for this TOPL automata. But that's future work. And finally, we implemented a tool based on this that does runtime verification. Now, the main reason I worked on the tool was that when you do theory, you focus on these concepts that you think are important, and you shove everything else away, which is nice to focus on the core of the problem. But sometimes you can convince yourself that the core is something that does not include a little tweak, which in practice makes the difference between being able to implement it or not. So for example, it could be that the overhead is prohibitive. So we ran some tests on the couple, and even though we did not pay attention to performance, the overhead was reasonable. So I mean, the runtime increased something like twice in the worst case, or 1.5 times. I mean, it's a big overhead, but still something reasonable, something that we know we can optimize to something good. Finally, what comes next? Right now we're working on a static analysis tool that specifies properties in the same way. That's gonna be pretty cool, I think, because of it's designed to work on big programs. And the other thing is that while I was testing this tool, sometimes I felt the need to be able to store sets of values in registers rather than single values, in order to express some properties that are not able to express otherwise, but more often in order to be more succinct. So Nikos Velekos and I investigate a little bit what would mean to have sets of values from a theoretical point of view, but that is not yet implemented. Finally, some of the most important references about this kind of work, I think, are well, the finite automata ones, Clini and Rabin Scott. Then you have the article that started this work on infinite alphabets, Kaminsky and Frances. Then runtime verification kind of took off, I think, with trace matches in 2005. And another good implementation is java.util. The paper here by Roche and Chen is a bit more theoretical and presents this slicing mechanism in a very nice way. But some other people like Baringer and et al. So that slicing is not quite doesn't cover all the things that you might want to say, so they design yet another mechanism called quantified event automata. And recently we studied one simple addition to register automata, this history register automata, which makes them extremely expressive and still retains many decidability results. That's all.